Hello everyone, I'm Christopher DeBella and I'm a staff software engineer at Codeplay Software where I work on the Compute CPP runtime. Compute CPP is a programming library for, it's an implementation of the SYCL programming library, which is a Cronus standard that's a little bit higher level than OpenCL. Before I continue, I'd like to thank my co-authors, all of whom have been critical for the success of the papers that we've written and what the implementation that we have and what we've presented to the C++ community. Now, today we're going to be talking about, we're going to quickly go through the STL at a high-level design. Then we're going to look at the Saxby BLAST primitive, before we look at the problems with the STL when we touch parallelism. And then we'll look at how views can assist with making things called parallel ranges, and then we'll actually explore what parallel ranges are. So programming on heterogeneous devices has been quite a difficult activity because there's additional things to worry about, such as deadlocks and race conditions, and we've traditionally been using things such as low-level APIs like OpenCL or CUDA, but higher-level APIs such as SYCL have started to appear in recent times. But optimizing for these systems can be quite difficult as well because you'll be working with a variety of different heterogeneous devices, all of which have different hardware characteristics. And so when you need to transfer data, if you don't, from one device to another, if you don't do it well, then you can suffer performance hits. And the Parallel STL, which is included with the C++ standard library, can offer a way to mitigate this because the algorithms that the Parallel STL offers are computational patterns that are decoupled from the domain that you're trying to solve. And an expert on that writes code for a specific device can implement the algorithm itself, which is orthogonal to what you need it for, and you can just transparently use it for whatever domain-specific application you're using it on, and you just provide a functor to customize the particular bits of behavior that you actually need. So can I get a show of hands here? Who's familiar with C++, please? Okay, sorry, let's invert that. Who's not familiar with C++? Okay. So I can probably fly through this crash course then. Who's not familiar with the STL design at a high level? All right, I'm going to be going through this very quickly then. So the STL is built up on three core components. It's a part of the standard library, and the three parts that make up the STL are containers, algorithms, and iterators. So a container is an object that owns or stores collections of other objects. And we have vectors, which are sequence containers. We also have lists, which are sequence containers. Vectors are contiguous arrays, whereas lists are doubly linked lists. And we also have associative containers such as map. There's unordered associative containers as well, but I haven't put any on screen. What ownership here means is that we have a means of controlling allocation and deallocation. This is done through constructors, destructors, insertion, and erasure. And then we have algorithms. So these describe operations on containers and other sequences. I'll come to what these other sequences are in a moment. There are three kinds. There's non-modifying, modifying, and sorting. So I've put a few up here. Can I get a show of hands? Is there anyone that's not familiar with any of the names on screen? Okay, so I heard about IOTA. So IOTA is something that was introduced in C++ 11. I think the name was taken from the APL programming language. It, for whatever reason, didn't make it into C++ 98. Basically, what you do is you provide a range. So you provide a beginning and end, and then a starting value. And what it will do is it'll fill up the entire container or the sequence with that value, and then incrementing by 1. So if you provide 0 and you have a vector of size 10, then the first element will be 0 and the last element will be 9. Does that answer the question? Okay, cool. And I should probably point out here, if you have any questions, please feel free to interrupt me. I will get to you when I have a breakpoint in my session. So we also have iterators, and the implementations, the internal layout of different containers are what make them unique. So the implementation for a vector, which is a contiguous block of memory, is going to be very different to a list, which is going to have a series of nodes that will likely be in arbitrary points of memory. And if we wanted to perform find on both of these, then we could naively go about it and have two separate implementations of find. But then we'd also need to have one for dec, and one for forward list, and one for any other kind of container that we can think about. This isn't great because that means that there's going to be n implementations of find, and we shouldn't have to write that many, because the idea of performing a linear search is going to be the same no matter how many containers we have. We're always going to be traversing through a sequence of elements, and we're going to be looking at a particular element, one element at a time, and checking that against some sort of given criteria. There's no need for us to actually have n implementations of find. So what we can do is we can use iterators, which are a generalization on pointers, to abstract over how we address elements. And iterators have a number of different operations. The most important ones are accessing elements, which we call the source function, and the successor function, which takes us from the current element to the next element. Now, not all iterators have the same operations. For example, output iterators don't have a source function. They have what's called a sync function, and the sync function is how we write to an element. And if we have what's called a mutable iterator, then we have both a source function and a sync function. And then we have bidirectional iterators, which let us move forward and backward. But of course, an iterator for a forward list can't take advantage of that, because forward list is a singly linked list. They can only move in one direction. So are there any questions on anything I've covered so far? Wonderful. Okay, so ranges are something that have been in C++ in terms of notionally for a very long time, but they are coming to C++ 20 in a much more formal definition. So they're an abstraction of containers that allow for uniform access, similar to how iterators are a uniform way of abstracting over addressing particular elements. There's two main operations that we care about. Begin, which returns an iterator to the first element in the range, and end, which returns a sentinel to the range. Now, a sentinel is something that's only been introduced very recently, and it's something that is related to the iterator that begin would return. And essentially, it's a way of saying this is when we've reached the end of our sequence. So typically, what you would have is for a vector, if you were to call end on a vector, you would get back another iterator, and when the two iterators meet, then you've said I've reached the end of the range. But if you were to work on an input stream, for example, then the way you're going to determine that you've reached the end of your input sequence is perhaps if you've reached the end of the file, or if you've lost the device and you've now got a bad connection, or you've got some sort of input failure. Typically, this would be done using an iStream iterator that's just default constructed. But now we have other ways of doing this, which is called a sentinel. Another way of applying a sentinel is for you to use an integer and count down from a particular number to 0. So let's say that we had a vector of 100 elements, but we only wanted to iterate over the first 10. We could just pass in the integer 10. When that hits 0, that means that it stops iterating. And this is the notation that we use for denoting a range. So what we say the beginning of the range is reachable. So the end of the range is reachable from the beginning of the range. So are there any questions on ranges? Okay, great. And this is the usage. So here we have the traditional C++ 98 way, where you provide a beginning and an end, and you check that they're not equal. And then the proposed way in C++ 20 is for us to just have a v. So it's a little bit easier to read here, because we're just saying let's find x in the whole of v. So it's quite a bit nicer. They're both still operating on a range, and we still get back an iterator from this find here. The only difference, well, there's a couple of differences that I'm not going to go into, but the major difference for this talk is that we're just going to be passing in a v instead of a pair of iterators. All right, so SAXPY is a level 1 basic linear algebra subprogram primitive where we provide two vectors as input, x and y, and a scalar alpha as input as well. And the result will be that the vector y becomes the sum of ax plus y. And now let's take a look at how we would implement that using the STL. So what we do is we've got our two vectors here, x and y. We've got our scalar a, and then an output vector. And what we're going to be doing is we're going to first use transform to map the to map x into out, where we multiply a times the ith element of x. Is there anyone in the room that's not familiar with lambda syntax? Okay, cool. And then what we do is we map the result from out and the elements found in y back into out, and then we sum them together. And this can be simplified a little bit using the new range-based algorithms that I've just mentioned. Well, we only have to provide the actual containers because they denote a range. And so we also have the parallel algorithms that C++17 introduced. So there's a proper subset of algorithms that were overloaded in C++17 to take an extra argument that allows us to take advantage of CPU parallelism. And whilst the semantics are typically expected to be the same, the complexity is wrong way. The complexity is somewhat relaxed, and what we do is we provide a starting parameter, the first of which is either par seek or par unseek. So I've chosen par and par unseek. This one here means to execute in parallel, and this one here means to execute in parallel and also make things are allowed to be unsequenced. Now this means that we can achieve vectorization with the STL as well. But otherwise, they're still doing the exact same thing. So, are there any questions on this section here? Okay. And just to make things a little bit easier for slides, we'll say parallel whenever parallel algorithms are being used. So now let's talk about the problems with the STL interface for parallelism. So it's not perfect, and there are a number of problems. The first of which is that we need to have a temporary variable when doing things in parallel. And what we've got here is we have an execution policy, but unlike on the previous slide where we have par and par unseek, we provided a SYCL execution policy, which lets us work on the GPU or on a different device so that we can take advantage of heterogeneous programming. And one of the big problems here, other than having a temporary variable, which is bad for accelerators because we have extra storage we have to worry about, and then we also have to perform extra loads and stores, which will eventually cause problems. But on top of that, we then also need to copy our data, so x and temp, to the device for computation. And then once the transform finishes, it implicitly gets copied back. So the user isn't actually aware that this is happening. And if you don't keep this in mind, then you will be incurring these copies. But it doesn't just happen here. We also get the implicit copies on the second kernel because we're doing two kernels and we need to get the data back onto the GPU. So let's take a knowledge of SYCL and of the C++ lifetime rules to see what we can do to mitigate that. So first of all, notice the buffers in bold. A buffer is like a container in that it owns its objects, but it resides on the device, and so we explicitly create them and initialize them with the data in our x and y, and only after they go, so they're copied to the device, at the first use of an execution policy, and then they're only copied back once they go out of scope because the destructor is invoked and then everything is returned. And you should notice that we're passing iterators to the buffers rather than to the vectors x and y because for implementation reasons, passing the iterators to the vectors would be invalid. And finally, we still need temporary storage because we haven't actually done anything about that. That wasn't the problem that we were trying to solve on this slide. But we can cheat a little bit and just put the temporary buffer on the GPU. So instead of providing a data parameter like we have up here, we've just provided the size, and that tells the buffer not to do any copying to or from the device. And the reason that we have the temporary buffer is because we have two separate kernels. We need some way of communicating between them, and the buffer is the way in which we do that. So if we wanted to completely remove that, we now need to use the two input parameter transform, which also takes a slightly modified kernel, which now what we've done is in the previous example where we had the multiplication here and the addition here, we fused them together manually to form one kernel, and that means that we can completely eliminate the temporary variable and everything that's wrong with it. So are there any questions about this? Yep.
Is there any limitation on the buffer?
Is there a limitation on the buffer? I'm not too sure on that, but I can get back to you after the talk about that. I'll chat with some colleagues and let you know.
It would be nice to see that. However, I'm aware that there is a strict limitation of what kind of sizes and what kind of layouts you can.
Sorry, I didn't catch that.
So there are certain limitations of what kind of data and what kind of formatted data that you can copy to the GPU.
What kind of? So you're asking, if I understand you correctly, you're asking what kind of formatted data can we copy to the GPU?
Yeah.
Okay, I think I will be answering that in the next slide. So if you can hold 30 seconds and let me get to that.
Great.
Okay, so the problems with the STL interface are that it's not composable. And let's now move away from Saxby for a moment. We will be coming back to Saxby in a little bit because it's simple and we can show things off with it. But let's take dot product, for example. Who here in the room is aware that inner product is an algorithm in the standard library? One hand, that's excellent. So, if you wanted to compute the dot product in two vectors, then you need to be aware that inner product is a valid way of computing the dot product. Otherwise, you're likely to end up using transform and accumulate in that order, or you're going to write your own dot product algorithm. And that's not really composable. We want to be taking advantage of as much as we can, but there's not always going to be an algorithm that can save the day. And so we're going to get performance hits otherwise. And let's take transform and transform reduce. Is anyone familiar with what transform reduce does? Okay, transform reduce, I saw a few nodding heads and one hand. So for those that aren't familiar, transform reduce is a map reduce operation. It's a really important operation. I suggest you go and take a look at it in the break. But basically, if you wanted to use transform reduce in or transform with more than two inputs, what you'll need to do is and only use one kernel. Then what you'll need to do is you'll need to convert the format of your data structures into an array of structures, and this has negative performance implications for both CPUs and GPUs because CPUs don't really like it, and we can't perform vectorization as asked for by par unseek because typically vectorization likes things to be in all of the same type. And on a GPU, this is problematic because we're not going to be accessing coalesced memory areas because the memory is no longer in a contiguous format. Does that answer your question?
Yeah.
Okay, wonderful. So now let's take a sidestep and talk about views. Who's heard about views? Okay, great. So views are something that are a part of the idea of ranges, and they are also being proposed for C++20 alongside the algorithms that are range-based. And so they're a special kind of range. They don't own anything, and they have constant time operations for copying, moving, and assignment. So a vector is not a range. Sorry, a vector is a range, but a vector is not a view because it owns things and none of these operations happen in constant time. Views are also typically lazy in nature. This talk really only cares about those lazy ones. And here's an example of how we can leverage views. So this is back to the find example. If we want to do a reverse find, typically in C++, what we'll do is we will pass a reverse iterator to the beginning of V, and then a reverse iterator to the end of V and the value. So that's how we would typically do it in modern C++ today. And with views, we can simplify this a little bit. So we can pass in V, because we're really only going from the beginning to the end, as we said before. But we can also use this compositional notation here to say that we want to view the vector in reverse order. And I'm going to demonstrate this a little bit more using the Saxby primitive that we've been talking about. So we have our two lambdas for addition and multiplication. And then what we have is a description. So because views are lazy in nature, we're not actually going to be doing any computation at this point. All we're going to say is, I want this to happen, but I don't really want it to happen yet. And so what we're doing is we're zipping our scalar A with the ith element of x. And so that's going to happen repeatedly for the entire range of x. And then what's going to happen is we're going to multiply the first element, A, times the ith element of x. So that will give us a result back. And this notion of and then is from the composition operator. So the composition operator, if you're familiar with Unix shells, then you'll possibly know it as the pipe operator, basically says, I want this to happen, and then I want this to happen, and then I want this to happen. So we store this first bit in a variable called ax, and then what we do is we zip the ith element of ax with the ith element of y. And then what we do is we add the ith element of x to the ith element of y, and then we turn it into a vector. So what this to vector bit here does is it says, I want this to actually materialize to be something. So all the computation happens when we get to this to vector bit. And so that means that we've just described how Saxby should work, and we haven't really got any temporaries. We've just described everything happening all in one point. So are there any questions on this? Great. So the SYCL parallel STL is an implementation of the parallel STL using SYCL, and we're using Compute CPP as the backend for the SYCL parallel STL, and we're also using the C++11 compatible Range v3 library, which is the sort of like the workshop for all of the Ranger stuff that's going to be ending up in C++. So these are both open source, as is this parallel ranges prototype that we have. They're all on GitHub, and this link will take you to the parallel ranges implementation. So here's an example of Saxby, again, using parallel ranges and using SYCL. So first of all, what we do is we have yet another execution policy. So this is different to the execution policy that you'd seen previously. What we have here is one that holds all of the metadata, and that's enabled by this copy here. So it holds all of the metadata necessary for you to perform everything, and that way we only get the copying happening once. And so it's virtually the same as it was in the previous example. The difference is that the main difference is down here, where we have this parallel transform that that does everything. So in the previous example, we had the 2 vector that materialized everything. Because we want everything to happen in parallel, we need to do this slightly differently. And so we pass in everything to our parallel transform, and it materializes everything. But despite the fact that there are five views here, there's only one algorithm. So one algorithm means one kernel. And that means that we've only got one thing. And this is the LVM intermediate representation. So there's a few operations here. First of all, there's a few loads, and 2 floating point operations, and 1 store. But notice that there's no DRAM operations at all, which means that we're not actually using any temporary storage. All we're doing is we're using registers to do all of our computation. Is there any questions on this stuff? Yep. So the question was, can you use buffers instead of vectors if you want data to persist on the device? I'm not 100% sure on that. I don't see why not, but I'll need to get back to you on that. And here are some results for using SYCL for using parallel ranges in contrast to just using the other parallel version of Saxby. Or not just Saxby, actually. We've got 5 different algorithms that we've computed. And so we've got increasing data sets from left to right per graph. And we've done computations on Intel CPU at the top and Intel integrated GPU down the bottom. This is the baseline, so everything is a speed up, which means that higher is better. And we've seen up to 3.5 times the improvement just by using views for kernel fusion. So program composition does make a difference. What about when there's no predefined function? So let's take the Mandelbrot set and use the computation and visualization algorithms to demonstrate how we can still use views to take advantage of parallel programming. So what we have here is we have our host image, and we've also got a GPU image, which is going to be on the device. And and the way in which we're going to compute this is we're going to use indices to the image as data points to do our transformations. And the way in which we describe this is to take IOTA. And so I explained what IOTA does before, but that was the algorithm version of IOTA. This is the view version of IOTA. So what we do is we just provide a start point, and then what we say is we want to take n number of integers from the start point, which is 0. So I can't remember what the number is, but it's going to be the size of the image. That's how many integers we're going to take. And then we use calculate pixel to determine the color. So this is a function object that basically determines the color based on how long it takes to work out if something is in the set or not. So are there any questions on this particular section? All right, so there's no parallel version of IOTA, and there's no way to do both transform and IOTA together, which is a bit of a shame. But what we did was we took the Intel Parallel STL and compared it against the parallel ranges using SYCL, and we noticed that even though Intel's Parallel STL is highly optimized for CPUs because it relies on thread building blocks, we still get up to a 3 times speed up just by using views. So in the future, we'd like to continue to explore these parallel ranges using Fusion, and we'd like to pay close attention to how we can look into data structures and how reflection might might help there. We'd also like to continue to see how they can be used to shape the C++ standard, and also how we can have SYCL be influenced by this as well. And finally, we'd also like to look at ways to refine standard tuple, which in our experience hasn't been able to be a standard layout type, which does cause problems for heterogeneous programming. Perhaps with the up-and-coming reflection research and the reflection technical specification, we may be able to get around that altogether. And just a shameless plug for Codeplay and CPPCon. If you're more interested in learning about SYCL, some of my colleagues will be giving a class for 2 days after the conference titled Parallel Programming from Modern C++, from CPU to GPU, and I'll be giving a class on generic programming with concepts and ranges. So if you're more interested in learning about ranges, then please come to that class. I should note that parallel ranges won't be featured in either class because that's still very experimental, whereas these two classes focus on things that are significantly more stable. So in conclusion, ranges help us to exploit parallel systems by giving us easier ways to compose programs, and they give us potential speedups where we may not have had those speedups before, just by writing cleaner and clearer programs. I'd like to thank you for listening, and I'm happy to take any questions until the end of the allotted time.
Thank you very much.
I have one question regarding linear algebra. You showed the example using Saxby.
Yep.
And I wanted to ask that have you considered picking up or rejuvenating the Valorate type for giving a DSL to linear algebra? Because Valorate does allow kernel fusion, so to say, and GCC does do it, but the interface to Valorate is not the nicest for some uses. But the internals can easily be implemented using these ranges primitives. But the user would not see the ranges, only the nice operators.
So the question is, if I understand correctly, Valorate is an existing thing in C++ at the moment. It has a series of operations, but the interface isn't exactly nice. And you'd like to know if we've done any research into sort of revising how Valorate looks.
Yes.
So we haven't done any research into that. We did, I think, have one very short informal conversation about Valorate, but I don't think that that led to anywhere. I can certainly take a look a little bit further into that, but no research at present has been done into Valorate.
Okay, thank you.
Any further questions?
Thanks. I'm just wondering, have you done any analysis of the overheads? There's seem to be quite a lot of data management on top of this execution layer. So what would be the cost of that?
So overheads,
especially if you're targeting GPUs.
So overheads with respect to what, sorry?
Well, if you go back to the Saxby slide,
so
the implementation, no further.
There were quite a few Saxby ones. Is this one you're talking about?
Yeah, that's okay. So basically you have the transform line, which is doing the computation.
This one here?
Yeah, and the others. And you make copies, and you have the repeat, zip, etc. So I'm just wondering what would be the cost of those operations in runtime, like
right?
Percentage-wise.
So I haven't gotten any numbers for you. This is what the output of that looks like. I'm not an intermediate representation expert, so I've had to consult with colleagues on this. But none of this is actually happening until you ask it to happen. So it'll only ever happen once, and that'll be on the GPU. And it wouldn't be, at least I don't expect it to happen any more. So I don't expect there to be any more computation than if we'd written this by hand. I'd certainly hope there would be less, but I haven't actually done the benchmarking for that to give you a concrete answer. I can only give you my speculation there.
Okay, a last question. Oh.
Thank you. The standard requires us to provide data race free and deadlock free code when we use the STL. How you can compare iterator based or range based solutions here? I mean that if you have disjunct ranges, it's pretty easy to use the parallel STL. But otherwise, how we can do this?
Okay, so can you hang on to the microphone for a moment, please? I want to confirm a few things first. So if I understand you correctly, then what you're asking is, what you've said is that with range-based stuff, so using iterators or just providing a container, that will be fine. But what you're asking, what happens if you have your own custom container?
Either custom containers, or we don't just use a transform where we want to do something with individual elements. But what about we simulate the kind of state machines when we, or state automation, when we use the neighbor elements to read, to modify the current elements, and we do this in kind of parallel way. So it's harder to split the container for disjunct intervals.
Okay, I think I understand what you're asking now. I think this discussion would be better held over lunch, where we can sit down and have a conversation about this. Just so I can ask a few more clarifying questions, and then you can ask some follow-up questions. But I'm very happy to sit down with you at lunchtime and have a chat.
Okay, so we have to move on. So let's thank Christopher again.